The numerical age of a rock or an event is based on radioactive dating. So atoms that have different numbers of neutrons are called isotopes. And some of those isotopes are stable. They don't fall apart or decay. And that would be like oxygen. There are other isotopes that, because of the different number of neutrons in the nucleus, are unstable and they are going to decay. The decay of the isotopes is at a fixed rate. We call that rate a half-life. So for different isotopes of different elements, we know the half-life, and we can use that to determine the age of the rock. All right. So here's a definition of isotopes: varying numbers of neutrons in the nucleus of an atom. So some of them are stable, oxygen, some of the carbons, carbon C13 is, but C14 is not. That's unstable. It decays. We can use C14 to date items that have carbon in them or carbon-based bits we find, like coal and charcoal and pollen and sticks. So the radioactive decay process is a decay chain. We start with the parent, and it breaks down into daughters. Those can break down again and again and again and again and again till we get to a stable atom. So the decay continues until it stops at that stable atom. The parent then is the beginning, and the end is that daughter that is the stable end of the decay process. We can measure the half-life of an unstable isotope. So here, let's look at the example. In this example, there are 16 parents and 0 daughters. After one half-life, half of those parents are going to decay and turn into daughters. After another half-life, half of those 8 will be 4 left over of the parents, and now we have 12 daughters. Another half-life, going to decay again, have half of those, so 2 out of the original 16, and then down to 1. And eventually then we can, they would all decay away. The way we do it, the way we measure it is using something called a mass spectrometer. In this machine here, we crush the rock, we separate out the mineral that we want to date. We figure out the exact mineral grain we want to date, put it in this machine, and it measures the parent and daughter ratio, how many parents to how many daughters. And when we know the half-life and the ratio of parents to daughters, we can determine the age. There are different systems that we use. So the table at the bottom shows the different systems, the parents on the left and the daughters on the right. The main one that's used, or that I've used in the past, is like this uranium lead, U-235 decaying to Pb-207. That one has the shortest half-life here in the table, 713 million half-lives. And we use these for a mineral called zircon that we're trying to date, in the millions, hundreds of millions of years. So the date then that is calculated or measured from the half-lives and the parent-to-daughter ratio is called the radiometric date. And that date represents the time at which those isotopes started to decay. So that's the time of the crystallization of that mineral. If that rock is reheated, the clock can be reset. So it can get very complicated with trying to figure out exactly what you're measuring. For igneous rocks, then, it's measuring from the moment that magma crystallizes, those zircons, for example. For metamorphic rock, it would be the moment that metamorphism happens. For sedimentary rocks, then you're measuring If it's a classic sedimentary rock and you have a mineral in that classic sedimentary rock that you can isolate, you're going to be determining the age that that mineral crystallized. So it's not the age of the sedimentary rock. It's the age of the original rock that then eroded to give you that clastic sediment. So maybe a sand grain on the beach in North Carolina, we could trace that back to a rock in the mountains in Boone, right? Okay, other ways that we can look at numbers for the ages. One of those is dendrochronology, and that's counting up tree rings. So in this image, there's a live tree. It's got a growth record with the tree rings, and there is a dead tree that is sitting on the ground that has a record with its tree rings, and then a tree that is underground, maybe like in an alluvial fan would be a common place to find like a buried tree. If we take the record from the buried tree, the dead tree, and the living tree, and we look really closely at the rings, we can isolate times that match up. So in here, the living tree matches up with the dead tree. That dead tree's life overlaps with the buried tree. So you can count the width of the tree rings. Another thing to look at, here's a giant clamshell, is the growth of the clam. Each of these lines on here represents a layer of growth of that clam. So we can count back those layers and figure out, put a number on an age of like how old is that layer within the clamshell. And then over here on the right is kind of a stratigraphy of the snow and a glacier. And each of these layers may represent a year, and the dark layers would be maybe where the area was dry and wind blew sediments up onto the glacier. And so it marks the dry time where the wind was blowing sediments around each year. We can count those and come up with a stratigraphy in that glacier. Then if there's a layer that has a distinct ash horizon, you can date the minerals in that ash, and it could be from a volcanic eruption. So you can get good dates from the layers in a glacier. Another way to measure time is with magnetostratigraphy. When we studied in the past, our knowledge of seafloor spreading and mid-ocean ridges and how we came about with plate tectonics, one piece of evidence was at the mid-ocean ridges, as that basalt crystallizes, the iron-rich minerals are going to crystallize with a orientation related to the Earth's magnetic field. So that happens everywhere, not just at the mid-ocean ridge. So in this image here, we've got layers that are recording the polarity of the Earth's magnetic field, and we can relate those to what we know from the past polarity and figure out that sequence, usually pretty accurately, and determine the age of those layers, and then that would tell us the age of those sediments. Then if you have a fossil in one of those layers, it's just a bonus, and you have worked out the stratigraphy and the absolute ages in your rock column there. Okay, so geochronology is going to be less useful for sedimentary rocks, right? Because if you wanted to date the class in that sedimentary rock, you're going to be dating the crystallization of a magma from a pre-existing rock. But what we can do with sediments is bracket those layers with rocks we can date. Like in the image here on the left, we can date volcanic ash, we can date this dike of basalt, the Cretaceous sandstones. We figured out the age of that because of the fossils in them, and then we can also determine the age of this granite, usually again through zircons. So once you can get the granite age from radiometric dating, the fossil age from the fossils found in the sandstone, the age of the dike, the age of the ash, then you can come up with a chronology and bracket the age of sedimentary rocks, narrow it down, get more and more data over time, and figure out the age of those rocks. The Earth is 4.6 billion years old. The oldest rock, and we can figure that out from meteorites and pieces of the moon. The oldest rocks that we found on Earth is 4 billion years old. Remember, Ga is billion years old. We have found these really old rocks. They're really old rocks in Australia, New Zealand. They're really old rocks in Canada. And dating those rocks, we have found 4.4 billion year old sandstones. So the grains in that sandstone are 4.4 billion years old. The oldest actual crystallized rock, like a granite, is 4 billion years old. Very old. And here are meteorites, a stony meteorite and an iron meteorite. All right, the last slide in the PowerPoint presentation is this one, and it kind of is a summary. I'm not going to go through the parts of it, but it talks about figuring out ages and those relative and numerical ages that we can determine to tell the history of the Earth.